Thanks for inviting me to speak here. So Filtronic is a company that's been around for many years. It was established in the late 70s, and we are located in the northeast of England, and perhaps unusually, we actually design and manufacture all of our products here in the UK. So I'm really going to focus on a section of 5G, which is the backhaul part of it. So we've heard a lot about access and the various other applications for 5G, but I just want to talk really about how all of that data gets backhauled into the main part of the network. So I'll talk a little bit about, just to explain exactly what backhaul is, the impact of 5G on backhaul. We've heard a bit about spectrum availability, and that's very important. As Helen mentioned, the only way to get extra capacity is really through more bandwidth, and to get more bandwidth, you've got to go to higher frequencies. So I'll talk a little bit about that. Even when you've got more bandwidth, then you need to find techniques for making use of that efficiently. So that could involve using very high order modulation techniques, or using multi-channel line of sight MIMO, for example. I've got a few slides on mmWave technology. Perhaps Liam's already covered some of the information there, but I'll go through those quickly. And then I'll talk a little bit about transceivers, a bit more detail about the transceiver requirements. So for backhaul, the bit I'm focusing on really is the macro cell, not the street level, but the base stations talking back into an aggregation point where it can go into the fiber network. So that's sort of to set where we are. I'm not talking about the access bit. I'm not talking about how smartphones talk to base stations. I'm talking about when you look at a base station, you'll see a dish usually, and that dish will be backhauling microwave data into the core network. Now you might think all of the backhaul is done with fiber, but that really isn't the case. Well, certainly not in most of Europe. So this is some stuff that I've taken from an Ericsson report here, but this is showing that basically over 50%, or around about 50% of all backhaul is done through microwave links. And they can be at various frequencies, traditionally from 6 gigahertz up to 40 gigahertz at the moment. But there's a strong move to push those frequencies up, and we're now selling a lot of links at E-band, which is 71 to 86 gigahertz. And the reasons for using microwave are pretty obvious. If you want to lay new fibre, then you're talking 30 to 80,000 pounds a kilometre. And that's ignoring the fact that you have to get planning permission and way leaves to put the fibre in. And in some cities, especially old cities, you can't even put the fibre in. So microwave is very attractive. In countries like India, about 85% of all backhaul is done through microwave. So it's a huge market. This shows in China, for example, that the situation is reversed. They do have a lot of fibre that they can use, and so a lot of the backhaul in countries like China is done through fibre. So the traditional microwave bands, as I mentioned, are sort of 6 to 42 gigahertz, and they're all small bands. If we go above 40 gigahertz and we go to E-band, then there's a huge chunk of bandwidth here. So there's only 15 gigahertz of total bandwidth available below 42. But if we go to E-band and V-band and even W-band, that's another 21 gigahertz of bandwidth that's available straight away. This is how the bandwidth is currently used. So you can see E-band is very small at the moment, just about 1.1%. The majority, there's a large chunk at 15 gigahertz, 18 gigahertz, etc. But these bands are becoming very crowded now. So you can see existing deployments here. There's a few blank bands, and some of these have been earmarked for 5G various applications, including access, and Liam's mentioned some of these lower bands. The main interest on improving backhaul capacity is coming at the higher frequencies. Not so much V-band, because V-band is a bit of a free-for-all at the moment. The licensing situation is quite complicated. You'll hear it said that V-band is license-free, but that's not quite true. It's license-free in America and Canada and parts of South America. Most of Europe, the whole of the band isn't license-free. It's used for other things. And certain countries like Russia, it's fully licensed. So 60 gigs is a bit complicated. And at the moment, there's about just 0.2% of links are at 60 gigahertz. And this is another form of the slide that we've seen in previous presentations, just showing exactly what's expected of 5G. And really the area that we're focusing on for backhaul is the throughput. So if we're going to have 10 gigabit per second in the access network, all of that data somehow has to get channeled into a backhaul. And the density, so there's going to be a lot more links, shorter links in a smaller geographic area. So I won't dwell on this actually. This is probably covering stuff that's already been talked about to some extent. But there's a sort of a land grab going on at the moment, whereas a lot of the bands, even up to E-band, are now being talked about for 5G access. Now, personally, I don't ever see your handset working at a frequency above, well, I'm a bit surprised if it will work at 28, but some people seem to think that they're going to have E-band links to handsets. I think that's probably unlikely. So this was an Ofcom study, and it named the sort of the top bands for 5G based on present usage. And you can see that, we've got bands up here which have been talked about, but E-band even picked up here has been quite popular. The FCC have recently unlicensed the V-band and pushed that up to 71 gigahertz. Right. So I suppose what I'm saying is here that there are threats now to the fixed service bands, to the backhaul bands, coming from allocation of the 5G bands above 6 gigahertz. And there's a statement here from the president of the ETSI mmWave wireless transmission group, sort of making the point that any discussion about spectrum for 5G must consider the operator's need for backhaul, not just for 5G in the future, but for the existing 3 and 4G. So if we start reallocating bands for access, it's going to cause problems with the existing fixed infrastructure. So how do we increase the bandwidth? So I've borrowed a few slides from this group, and this is a useful information resource. So the ETSI have a mmWave working group. It's not part of the official specification group, but there is a lot of work going on, and a wide variety of companies participate in this, most of the major OEMs and the operators and component manufacturers. I'll give a bit more details of that later on. But so these are ways to increase the capacity. So there's addressing the network topology, I won't dwell on that, but increasing the bandwidth for backhaul. So we can either use multiple bands, we can increase the channel bandwidth. To do that, if we use the lower frequency bands, you're still limited to 100 megahertz, maybe 200 megahertz of bandwidth. If you want real increases, then we need to go to E-band, and in the future, possibly even higher. So at E-band, you've got 10 gigahertz of spectrum available, and that can be divided up. So you can comfortably have 2 gigahertz channels at E-band. D-band is a new band that's under discussion. We're talking here about bands up to 175 gigahertz. So that's just to sort of reiterating what I've said here. W-band, there's a small band between 92 and 95, but really it's not really used very much at the moment. There's not enough contiguous bandwidth there. So again, we've probably seen some of these. The things to consider, though, if we go into these very high frequencies, are the transmission characteristics. I think Helen's already shown this slide, but basically there's an attractive window here at E-band where we're away from the oxygen peak, and you've got quite reasonable, acceptable levels of loss at E-band. If you go to D-band, it's actually not too much worse. Obviously, the losses are increasing, but it's not dramatically worse, and it's still quite usable. Rain fade is another consideration. So it's important. Operators like to have networks that operate 99.99% of the time, so less than 5 minutes outage a year. So when you're designing a link, then it's important that there's sufficient margin allowed for the worst anticipated level of rain. The bands at D-band, there's a number of small bands that have been identified. This is still subject to discussions within SE19 as to exactly how these will be allocated. But there's potentially another 30 gigahertz of spectrum available at these higher frequencies. There's just a bit more detail on the propagation characteristics at D-band. So rain attenuation, interestingly, is quite flat. Once you get above sort of 90 gigahertz, it doesn't get that much worse. So it's fairly flat. The other forms of attenuation do increase slightly. It's about 1 to 2 dBs higher in terms of gas attenuation at D-band. But the system simulations that have been done do show that it's quite feasible to design links that will work over several hundred meters, even up to 175 gigahertz. Perhaps too much detail here. This is the rain map, ETSI rain map, but you need to design basically for up to 42 millimeters per hour, which equates to about 16 dBs per kilometre of loss at E-band. Now that's only 5 dB higher than the rain attenuation at 40, but for a given size antenna, then you've got another 6 dB of antenna gain. So you get some advantage in going to higher frequencies just from the antenna gain. So a bit on how do you increase the capacity. So the two primary ways would be to increase the modulation order or to increase the bandwidth. Now, increasing the modulation order, this is the sort of error function typical waterfall graph, which shows the carrier to noise ratio that you need for a certain error rate for different orders of modulation. So if we're talking about QPSK here, you want 10 to the minus 6 error, then you need a carrier to noise ratio of about 13.5 dB. If you increase that, so you want to double the capacity by going to a higher order modulation, you go to 16 QAM, then you need to go from 13.5 to 20.5. If you want to double it again to go from 16 QAM to 256, then you need to go from 20.5 to 32.5. This obviously has a dramatic impact on the range that's achievable. This is all coming out of the link budget. So increasing modulation order, people talk about going up to 4K modulation, but you can see that you're going to have to increase the carrier to noise ratio dramatically for that to work. More efficient in technology terms is to go to wider bandwidth. So every time you double the bandwidth, there's a 3 dB impact on the range just due to the energy per bit reduction, and the wider bandwidth, the noise bandwidth increases. But you can double the capacity by doubling the bandwidth more efficiently than you can through going to higher order modulations. And that's typically the state-of-the-art links are operating at 256 QAM and at up to 2 gigahertz bandwidth. That will give a 10 gigabit per second capability. Now, we've talked a little bit about range. I don't know how we're doing for time. So just to put some numbers on what do we mean by range. So if there were no rain attenuation to worry about, and you have a typical amplifier of about 20 dBm, then even with 256 QAM, you're talking about over 10 kilometers range. Unfortunately, you have to allow for rain fade. So if you had 20 dBm output power here, and you take moderate rain fade here, this is about 14 or 16 millimeters per hour, then we're talking about a backhaul range of about 1.5 kilometers at 256 QAM. If we take the most extreme region, southern states of America, then you'd have to allow up to 40 millimeters of attenuation, and then you're down to about 600 meters. So you can increase the power. So if you can operate at closer to a watt or even 2 watts, then you can push the range up to closer to 2 kilometers. The increase is somewhat disappointing there. You see, that's massive amounts of extra power don't give you huge increases in range once you allow for rain fade, unfortunately. So for terrestrial systems where you've got horizontal links, that's a bit of a problem. But one application for E-band backhaul may also be talking to high altitude platforms, so actually going to movable points. So if you're pointing upwards, then of course your rain is usually only confined to the first kilometre or kilometre and a half. Once you're beyond that level, you're into much more favourable conditions. So you could talk about pointing to links up the sky at much longer range. So a bit of a trade-off then. So if we go to higher order modulation, as I've said, it's diminishing returns. The symbol rate only increases as log 2 of the QAM order, so that's not quite so attractive. And it places very severe demands on the linearity of the amplifiers, on gain flatness. If you wanted to use wide bandwidth, you want a nice flat channel, and phase noise. So to get these very low carrier to noise ratios, then you really struggle with phase noise. 256 QAM is quite readily achievable with today's technology. We demonstrated signal to noise ratios that would support 512 QAM, but it's as I say, diminishing returns. Wider channels consume spectrum, less of a problem at high frequencies because the spectrum's available. But it also has an impact on baseband. We're talking about quite 2 gigahertz wide bandwidths for the A to Ds and differential amplifiers at baseband, which is stretching the capability at baseband as well. And then the other way of doing it is multi-channel systems. So line of sight MIMO is one technology that is being looked at. XPIC, where basically you've got 2 transceivers operating on opposite polarization, so you can double the capacity of a link. You have to, of course, use twice as many transceivers at each end, so there's a cost penalty. Or multiband, so you could, for example, have 2 channels operating, and each of those channels could be cross-polarized, so you could get up to 4 times the capacity doing that. And there are published results recently, so we've seen results very recently published with 40 gigahertz per second links being established over about 4 kilometers, and even longer links, 36 gigabits per second up to 10 kilometers. So the trade-off there is in terms of cost. Multi-channel systems are inevitably going to be more expensive. So a bit to say, if we've got time, on semiconductor technology. Yeah. So Liam may have covered some of that, so I won't dwell on this, but basically, if we're talking about E-band and D-band, there's a range of technologies. GaAs is still dominant. It's the most mature technology. There are 6-inch processors available, 0.1 micron gate length, and they operate very well up to 86 gigahertz, and in fact, they have been pushed beyond that. So even the 0.1 micron processor has been used up to about 140 or 150 gigahertz. Indium phosphide is great for LNAs. There are some good indium phosphide-based LNAs with very low noise figures, down to 2.5 dB. GaN really hasn't, well, there are some GaN processors at E-band, but they're very expensive. I mean, you're talking about, well, I've been quoted figures of $1,000 a chip for a GaN PA at E-band. So it's not really there yet. In terms of VCOs, the in-gap HBT VCOs give very good phase noise, quite perfectly adequate for 256 QAM at 86 gigs. You'll see a lot of talk about silicon germanium, which is great. There's some really good, highly integrated silicon germanium chips available. Now, Filtronic is technology agnostic. We're not wed to any particular semiconductor technology. We'll use whatever's available and whatever works. But the fact of the matter is we have yet to find a silicon germanium chipset that will meet the specs that the customers are placing on us. If they did, we'd use it, but so far, every silicon germanium chip I've seen needs a GaN PA and usually a GaAs PA and a GaAs LNA in order to get the performance. BiCMOS is actually coming up very rapidly, and there's some quite impressive results being quoted on BiCMOS. But again, it's going to be limited in power. In terms of pushing the actual transmit power and getting efficient, very linear transmitters, one of the good things about the very high frequencies is that the waveguide is very small. So you can make a waveguide power combiner at E-band in a very compact outline. So here's a 2-watt E-band power amplifier that Filtronic have developed. So that's got a gain of 18 dB, and it's actually 8 PAs combined. Very efficiently though, because it's waveguide, you get quite efficient power combining. So this has a sort of a headline figure, the OIP3 of 39 dBm at 86 gigahertz. Don't be put off by the heatsink, by the way. That's just because we've got paranoid engineers who don't want it to overheat in the lab. In practice, that would be built into an ODU with a heatsink that would be built into the casework. I won't dwell on that. Different technologies have different applications. So we're seeing silicon can be used in some of the shorter reach applications. So small cell, for example, silicon technology is quite applicable. But if we're talking about macro cell and the longer range, then at the moment, 2016, 2017, it's still dominated by gas. That's really the situation for D-band. Again, we're talking about 3-5 semiconductors. And the technology is already there with indium phosphide, albeit at a very early stage, not commercially available, but the technology is there to go up to 175 gigs. Silicon's getting there, can probably go to about 160 gigs using the best by CMOS processors. Assembly technologies, Liam's touched on the fact that we still use wire bonding. Some people are surprised that you use wire bonding at these frequencies, but the important thing is really in the precision and the control. And the reason we can get away with it is because we do automatic die placement. The die are placed to within very high accuracy. The wire bonding is all automated. So although it has an effect, if it's uniform and it's predictable, then it can be compensated for. The other advantage is that we can mix and match technology, so we can put little quartz E-band filters in and mix those with gas chips, etc., and we can print filters. I'll skip over that. Liam's already touched on the effect of ribbon bond and V-bonds, so that's what I've mentioned about die placement. So our equipment will place die to within plus or minus 12 microns, which is what we need here. Okay, so very quickly, just to finish, if we're okay. Yeah. All right. So this is the insides of a transceiver. The unit here is the transmit unit. This contains the transmitter, the receiver, the diplexer, the VCOs, the PLL. It also has a microcontroller in there. And the microcontroller is used to set the frequencies. At E-band, we work on a predefined range of frequencies on 250 megahertz center frequencies, the 19 channels over each of the E-bands. So this takes care of all of that. The modem here is a very important part, obviously. And what goes on in the modem can compensate to a large extent to some of the impairments that we see for problems like phase noise and phase matching on the baseband. A lot of error correction algorithms in there. So you can get a fair amount of system gain with a very clever modem design that compensates a lot for the shortcomings at the microwave frequencies. So this is actually a reference design. So this is the part that we are manufacturing in volume. We probably manufacturing 600 to 1,000 of these a month. And we're working with Escape Communications. They have a modem design, and we have a reference design for an ODU, which you'll see on the display stand. So what's the key parameters within the transceiver? So PA linearity is very important. Phase noise I've mentioned. You need about minus 92 dBc per hertz at 100 kilohertz offset for 256 QAM. The best VCOs available at the moment are pushing minus 98, so the parts are available. Range is highly dependent also on noise figure. So 9 dB maybe doesn't sound so good, but that includes all of the diplexer loss and everything up to the antenna. So that's the noise figure reference to the antenna port. With an indium phosphide LNA, you could probably reduce that to 4 dB. In fact, you can. We've built receivers at 4 dB noise figure. Transmit power with a single amplifier, you're talking typically PSAT around 23 dBm. For special applications, you can use power combining and get up to maybe 35. Compliance with the mask, the ETSI masks, is important. So this is where linearity comes into the design. If you're going to meet this mask, which is defined for different modulation orders within the ETSI specification, this document makes fascinating reading if you're into this type of thing. So this will tell you what the mask compliance needs to be. And you can see it's quite severe as the modulation order rises. But linearity is one of the main issues that we face in trying to meet the mask with available power amplifiers. The other thing is that it's a relative mask. So you can see the noise floor is about minus 42, minus 43 dBc far from carrier. All of these systems have to have transmit power control, so you might want to reduce that power by 30 dB. Unfortunately, because it's a relative mask, the noise floor has to go down dB for the transmit power. So where you put the attenuation in the transmit chain is quite critical to making sure that the noise reduces as you adjust the output power. Okay, so one important point I want to make is that at these frequencies, I don't know whether we've got any component manufacturers here, but you can't trust the data that you find on the data sheets. They give you simple things like OIP3 and PSAT. It's pretty much meaningless if you want to design a real transceiver. So we characterize all of the chips ourselves, measure them on wafer, and build up, putting real data and real measured data into a VSS or similar model. And then we can look at the contributions. This was in case of linearity as you go through the chain. But the reason I say we need to measure things is if this is 4 power amplifiers from 4 different manufacturers, and this is the IMD versus output power for each of these. Now, if you think OIP3 is a useful measure, then sometimes it is. Often it's pretty useless. The OIP3 varies dramatically with output power. And different amplifiers, I think most of these are probably made on the same process, but even the design, you can have vastly different OIP3 characteristics. So if you're using the power amplifier to set the output power of the transceiver, then you need to know what the OIP3 characteristic is as a function of output power. And the other thing is they vary a lot with bias. So and depending on whether you fix the drain current or you fix the gate current. If you fix the gate current, then the drain current can increase quite dramatically as you drive it into the higher power levels. And again, that you can have some very odd OIP3 characteristics. And then the effect of wire bonding. This is a data sheet response with usually on wafer measurement. Once you add, these are actual measurements, once you add the wire bonds in, then you can introduce quite severe distortion to the characteristics. So again, you need to know about that. So if you're doing the characterization, it has to be done in a real circuit. Right, I think I'm probably getting to the end of my time. But the last thing is filters. So diplexers, we design diplexers, and we tend to integrate those into the module. We can also do multiplexers though. I mentioned multi-channel systems where you might want to have 2 channels, two 2 gigahertz channels separated by 3 gigahertz. So we have also multiplexers, so you can have an integrated transceiver with multiple channels. I think I've probably run out of time. So basically, wide bandwidth millimeter wave radios will provide the solution to increasing capacity in the backhaul network. We're already demonstrating fiber-like capacity of 10 gigabit per second using single channels, and multi-channel systems will push that up to 40 gigahertz. If we go to higher frequencies above 95 gigahertz, then the capacity can be increased even more. Okay, right, thank you.
Okay, thank you very much, Mike.
Right.
Yeah, Mike, thanks. Just on your earlier part of your presentation, you were talking about obviously the increase in the beatable capacity and going to different frequencies. And I just wondered if at some point in the future approaches like full duplex start to become, well, interesting or...
They are actually, yeah. One of the problems if we go to very high frequencies is it's really hard to make a diplexer at 75 gigahertz. You'd need to have machine tolerances of about better than 2 microns, which is getting hard. So there is work looking at doing away with the diplexer, just having separate antennas. But of course, the isolation between the antennas is an issue. So full duplex techniques are being talked about to overcome that problem. Yeah.
Already, people predict and use the data rate will be at least 1 gigabit per second.
Yeah.
If the backhaul data rate is about 10 gigabit per second,
Yeah.
would that be good enough?
I suppose we have to be careful here. That 1 gigabit per second to the handset is probably not a continuous 1 gigabit per second. It's very bursty in nature. So this is a technique you often, well, if we talk about point-to-multipoint systems, they quote quite high data rates, but in fact, what they do there is they're averaging the data. So you might get your 1 gigabit per second at a certain time slot, but you won't want that continuously for hours on end. So we're talking about an aggregated. I sort of got an analogy here, which I don't know whether I should go to the next slide, but I can't stop thinking about the evolution of the sewer system in London, which was basically.
Yeah, go on.
So we're talking about. Well, just to tell the story. So in the 19th century, the population of London grew very, very dramatically, but of course, the infrastructure wasn't ready for this. So we're talking about individual cesspits forming into creeks going into the Thames. So in the middle of the 19th century, Joseph Bazalgette realised this was a problem and built the system that's currently in place in London. So, and he did a really good job because that system has still got capacity for London, and it's only just being upgraded. And what worries me about 5G is he had a fairly easy problem, didn't he? Because he could work out how many people were, how much waste they were likely to produce, and then design the capacity and the diameter of the pipe to cope with it. 5G just seems to be wanting to run a mainline sewer to everybody's handset. and it is, and well, the analogy in terms of content is probably also quite appropriate, but we've got to be realistic about how much capacity you can put into the network. So I won't say food for thought, but never mind.
Hi, Mike. You mentioned beamforming at E-band for optimizing the connection. Is that happening today?
It's not so much beamforming because these are fixed links. It's multi-channels, so they're not.
But channel optimization.
If you go to line of sight MIMO, then that gets a bit more complicated. But the systems we've seen here are actually individual links. Their frequency, operating at different frequencies. There is work going on line of sight MIMO, but I'm not too familiar with the details of that.
There's a company in South Africa called Monitor.
Yes, indeed, yeah. And that comes into the full duplex because they need some kind of interference mitigation.
This one at the back there.
Thank you for the nice presentation. At the moment in RAN, there is an ongoing discussion in 3GPP on this sort of flexible functional split requiring basically next generation frontal interfaces, which are quite flexible, and they're going to evolve from one-to-one to many sort of frontal interfaces. So how do you see this sort of backhaul solutions, which are classically point-to-point, can evolve towards that vision of many-to-many basically frontal solutions with flexible requirements rather than having a strict, for example, requirements on data rate or bandwidth?
So you're talking about adapting to different capacities through adaptive modulation or adaptive channel?
Basically, both adaptive modulation and adaptive design in terms of many-to-many rather than having point-to-point links. So basically to enable statistical multiplexing.
I think there's quite a lot of work going on at 60 gigahertz in that area. So there's sort of various companies looking at sort of mesh. You're talking about mesh type systems. Yes, yeah. There are a few regulatory things associated with that because you need certain antenna gains, certainly at 60 gigahertz. So there's a bit of a dispute going on at the moment. The FCC have got a different set of rules to ETSI. At ETSI, you need a minimum antenna gain of 30 dBi, I think it is, which can be quite difficult for a sectorized or a switchable antenna. They tend to be quite low gain, probably 17 or 18 dBi. So I can see those things working at perhaps up to 60 gigahertz. I'm not sure about at E-band. I think that might be pushing it a little bit.
Okay, anyone else? Okay, thank you very much, Mike.
Okay.